Okay, thank you, Stuart. Yeah, I'm Yiyi Liao from Zhejiang University, and I'm an assistant professor in the university, and I'm currently co-chairing the adult group on Gaussian Splat coding and at MPEG. And this is actually a joint adult group between Working Group 4 and Working Group 7. And today, I would also like to share some of our thoughts from the MPEG side, and actually some of our thoughts are similar with the MPEG. So first of all, because this workshop is open to the public, and I assume a few of the audience may not be very familiar with standardization, so a very brief recap or overview or a very brief introduction about MPEG. MPEG is the abbreviation for Moving Picture Experts Group. And the main distinction between MPEG and JPEG is that we focus on video, and it was established in 1988, and it's a working group under ISO and NEC. Over the past 30 years, it has developed well-known standards such as AVC, HEVC, VVC for video coding, and also MP3 for audio coding. And this is the pipeline that we are very familiar with. We have the 2D video, and we perform like any of these standards for compression. This allows to achieve efficient transmittance and also compression, and also for storage, for efficient storage. And this allows us to viewing on device, for example, like on the laptop or the headphone. Yeah, so of course, with the rise of the immersive media like Radiance fields, we are also exploring the potential for compressing the 3D video. And actually, over the past few years, MPEG has already developed several standards for immersive video content. For example, like we have already standards for the compression of point clouds, mesh, and multi-view video. So over the past 5 years, there are several like related standards that are published. For example, we have video-based point cloud compression, and we also have geometry-based point cloud compression, GPCC, and we also have like MPEG MIF for multi-view video compression. And we also have MPEG VDMC, which is currently under DIS. And we also have started exploration experiments, which is called Yiyi experiments on the Radiance fields starting from 2022, where we started from NERF and now shifting towards 3D Gaussian. So here is a more detailed timeline about the explorations on Radiance fields. So we started the adult group on implicit neurovisual representations in July 2022. And over like a 2-year exploration, we've shifted to Gaussian Splat coding. So we basically closed this adult group and established a new adult group, which is currently a joint adult group between Working Group 4 and Working Group 7. Yeah, so basically the INVR adult group, it was originally started under Working Group 4, and we started like different Radiance fields representations starting from NERF, and also these representations that has already been introduced by the previous speakers. We started like these hybrid representations like Incident GP and TensorRF, as well as then shifting to 3D Gaussians. And yeah, so basically, in November 2024, we decided to switch completely to 3D Gaussian because it's just much more practical in terms of the real-time rendering. And over the past 3 years, we also studied different codecs for the compression of different representations. So initially, with NERF, it was just a pure neural network. So we also studied whether we can use a neural network codec for the compression. And also we investigated some dedicated codec tools for the compression. And later on, we also moved to the hybrid representation, and as we were in the video group, we thought it's actually also very reasonable to compress the feature maps using video codecs. And also this can be used for the compression of 3D Gaussian as well, because Professor Park also mentioned one of these methods like self-organizing 3D Gaussians, where you can put the 3D Gaussians into a 2D map, and this allows you to use image or video codec for compression. And now because like 3D Gaussians, they can also be viewed as one particular type of point clouds or a variant of point clouds. That's why the experts in WG7, they are also very interested in the compression of Gaussian spat coding. And that's why we have started this adult group on Gaussian spat coding. And now we are investigating both using video codec and point cloud codec for compression. So this is some more information about this joint adult group. Is leading by convener, the working group 4 convener Yiyi, and the working group 7 convener Marius Preda. And we have 4 co-chairs, 2 from working group 4 and 2 from working group 7. So myself and Guanbang from Etri, we are from the working group 4 side, and we also have Alexandra Zagato and Julian Ricard from the working group 7 side. So now let me share some of our thoughts on the standardization of the Gaussian splat. So this is also a very similar pipeline to what David just showed. So David has this model initialization here, and I have training here. So instead of now, so this is actually a pipeline that is quite oftenly investigated in the academia. So we have this model training, and we obtain some sort of 3D representation, which can be, for example, the original 3D Gaussians. So here I illustrate like several frames. So this is a video sequence. So we perform encoding and obtain the bit stream, and after decompression, we have the decompressed 3D representation, and we render it and we compare with the original ground truth images to see how the model performs, right? So many of the methods Professor Park has already introduced, and many of these methods, they actually follow this pipeline. And we were like, this actually introduced some challenges for standardization. So the first challenge that we think is that what was also mentioned by some of the previous speakers is that it's still under very fast developing, which means that, but when we think about the standardization scope, right? So what we want to standardize is what is there in the bitstream and how the decoder looks like, and what is the representation that we decode. And so this means without fixing the 3D representation, it's very hard to talk about standardization. However, the Gaussian representations, they are still under very fast developing, especially for the 4D things, like for dynamic inversive things. So this is very tricky question. And a second challenge is that the entangled evaluation in this pipeline. So existing works, they typically consider reconstruction and compression jointly. So they start from the 2D images and perform the reconstruction and the compression, and then evaluate the performance between the compressed image and the original images, right? So this makes the representation and the compression, they're highly entangled. And well, actually, in my personal view, if we want to achieve the best RD performance, it's true that we want them entangled. For example, we can train the model using like reconstruction loss in combined with for example, some entropy regularization, as Professor Park also mentioned before. However, this is all what we can do on the encoder side, right? But for the standardization point of view, what we care about is the decoder side, and those things happens during training. Is very hard to standardize. So this means that having everything entangled together may not be ideal for standardization. And also it's very hard to measure like how effective the compression really is if we have the training part entangled with the compression part. Because for example, if we just train the model differently, we might obtain a different 3D GS representation, and this leads to a different RD performance. And then it's very hard to tell whether the codec works better or what the codec works better or the training works better. And again, training is something about the encoder side. So to address these challenges, what we do in MPEG is that we now have 2 tracks moving forward. So the first track we have is called I3DGS. So this I3DGS means after training, we simply ignore the original 2D images. So we have already some models that are trained and prepared and shared among the entire group, which is the I3DGS sequence. This I3DGS sequence means per frame in real 3D Gaussian. So yeah, so this may not be the best representation for dynamic scenes, but this in real 3D Gaussian representation is also widely used already in industry, and we believe many of the dynamic representations can actually be converted to this per frame 3D Gaussian. So that's why we think this is a good starting point. So to address the second challenge of this entangled evaluation, instead of comparing to the original images, we directly compare the the decompressed images to the uncompressed images. So this allows us to measure purely the performance of the codec. Okay, so you may wonder, like, yeah, so the I3DGS may not be the best representation, right? So what should we do? So that's why we have the second track. We have the second track called A3DGS, and here we have the still allow people to explore different representations. A means like an alternative 3D representation that we don't know yet, but is still a sort of like a variant of the 3D Gaussians. So we will continue exploring this A3DGS representation. And if we do have good evidence that this alternative 3D Gaussian representation is better, for example, than I3DGS, then we will do the same thing again, like, for example, like generating the data and providing this to the group. And then the group can start it from the same A3DGS representation and comparing the codecs. So this means we will still have this disentangled representation and compression. And over the past 2.5 years, we have also collected quite some test sequences to cover different use cases that we care about. So we have this multi-camera setting covering forward-facing scenes as well as object-centric scenes. And we also have unbounded single-view video, for example, like this street scenes. And we also have this casually captured user-generated content like the single-view video. And yeah, so I think Professor Kanazawa's algorithm will be very helpful to reconstruct such dynamic scenes. And we also collected some software for the acceleration. So we have this GS Codec Studio, which is software highly inspired by the Nerve Studio and Splat. So we actually have this GS Codec Studio, which contains the representation, the compression simulation, and the post-training compression, as well as the rendering. And we also have customized rendering and evaluation software implemented. This allows us to easily compare the uncompressed model and the compressed 3D Gaussian model. And we also have this renderer, which allows us to visualize the 3D Gaussians in different modalities. And of course, there are still quite some open questions that are not clear and that still requires more explorations. So for example, like in this pipeline, what would be the ideal codec? So there are quite some alternatives, as I mentioned earlier. Like we can use point cloud encoder and decoder. We could also use video codec, and we can even build some dedicated codecs for this task. So which codec would perform the best for the Gaussian splat coding is still not clear yet. And another question is, should the codec support one representation or multiple ones? So if indeed in the end we figure out that we do have a I3DGS that is kind of representative, and then we have A3DGS that like performs better, like do we consider compressing both, or we just develop one standard for one representation? That's still like an open question to be answered. And finally, I would like to thank all the participants from different companies and universities and over the past 3 years for both INVR and GSC. And you're also very welcome to join us on this very exciting journey about the standardization of Radiance fields. Okay, and that's all from my side.